7 minutes ago, the Euclid Space Telescope transmitted a new batch of images that stopped astronomers mid-sentence. Not because they were beautiful, because they were wrong. Wrong in the sense that what they showed should not exist according to our best models of the universe. Structures too large, patterns too precise, alignments too deliberate. Scientists are not celebrating tonight. They are quietly asking each other the same question. What exactly are we looking at? What you are about to hear is not speculation. It is not dramatized for effect. These are the actual findings emerging from Euclid's latest data releases, and the scientific community is genuinely unsettled. Because these images are not just showing us new things, they are undermining things we were certain we already knew. Stay with me through every paragraph of this because the reveal at the end of what Euclid has just exposed may be the most uncomfortable truth modern cosmology has ever been forced to confront. Euclid was built for one mission above all others: to map the invisible architecture of the cosmos. Not the galaxies themselves, but the dark framework around which galaxies are arranged like ornaments on a structure no one has ever touched. Positioned 1.5 million kilometers from Earth at Lagrange point 2, Euclid's instruments were calibrated to detect gravitational distortions so subtle they require millions of galaxy measurements to even become visible. The telescope does not look at the universe. It interrogates it. And in its newest images, the universe has answered in ways no one expected. The latest data release covers a region of sky that, at first glance, appears to be a routine deep field observation. Thousands of galaxies at various distances, glowing in infrared and visible light, arranged across an enormous canvas of dark space. But when Euclid's processing algorithms began mapping the gravitational lensing signatures across this field, something appeared that forced researchers to run their analysis a second time. Then a third. A structure emerged from the lensing data that should not be there. A dark matter concentration of extraordinary mass located in a region of space where no corresponding visible matter exists. No galaxy cluster. No bright central core. Just an enormous, invisible gravitational presence bending light around it with terrifying precision. This object, if confirmed, would represent something cosmologists have theorized about but never directly observed. A dark matter halo without a host galaxy. A gravitational architecture that formed without igniting into stars, without collapsing into visible structure, without leaving any luminous trace. It simply exists. Massive, cold, and completely dark. The terrifying implication is not just the object itself. It is what the object implies. If dark matter halos can exist without galaxies, then our model of how galaxies form inside dark matter halos may be fundamentally incomplete. The chicken and egg question of cosmic structure just became far more complicated. Euclid's newest images also contain something deeply uncomfortable, hiding inside what should have been a routine observation of a known galaxy filament. Filaments are the enormous thread-like structures connecting galaxy clusters across hundreds of millions of light-years. They are a core prediction of the standard cosmological model and have been observed before. But Euclid's resolution is revealing their internal structure in a way no previous telescope could achieve. And what is inside these filaments is not what the models predicted. The density gradients are sharper. The dark matter concentration along the filament spine is more intense. And most disturbingly, there are perpendicular subfilaments branching off at regular intervals, spaced with a geometric consistency that has no current theoretical explanation. The cosmic web was supposed to be chaotic at small scales. Euclid is showing that it may not be. That geometric regularity is not a minor anomaly. It is the kind of pattern that, in any other field of science, would immediately prompt researchers to ask whether they are seeing the signature of a physical law they do not yet have. In cosmology, regular spacing implies a preferred scale. A preferred scale implies an underlying process. And an underlying process operating at the filament level, shaping dark matter distribution with geometric precision, would require revisions to the standard model of structure formation so significant they would ripple through every branch of theoretical physics. No one is making that claim yet, but no one is ruling it out either. Among the newest Euclid images, one in particular has drawn intense attention. A deep field observation targeting a region of sky previously catalogued as relatively unremarkable. What Euclid found there has been described by lead researchers as genuinely difficult to explain. The image reveals a galaxy cluster at approximately 6 billion light-years distance, which is itself not unusual. But surrounding that cluster, at precise distances in multiple directions, are gravitational lensing arcs that do not correspond to any visible background galaxies. The arcs exist. The bending of light is measurable and statistically significant. But the objects producing that lensing signal are not emitting any detectable radiation at any wavelength Euclid can observe. These are not dim galaxies. They are not faint sources requiring longer exposures. They are genuinely invisible at every frequency, yet massive enough to bend light around themselves with the force of a mid-sized galaxy cluster. What makes this finding uniquely disturbing is its location relative to the known cluster. These invisible mass concentrations are not randomly distributed. They are arranged symmetrically around the visible cluster in a pattern that suggests a gravitational relationship, as if the visible cluster and the invisible masses are part of the same large-scale structure, as if the dark matter architecture was already in place before the visible cluster formed inside it. Euclid is not just detecting dark matter in this image. It may be revealing that dark matter forms organized, structured systems that exist independently of visible matter, and that galaxies and clusters are simply what happens when gas and stars manage to ignite inside the pre-existing dark framework. The universe we see may be nothing more than a faint glow inside a much larger, completely invisible construction. The newer Euclid datasets are also generating serious discussion about dark energy, and not in a comfortable direction. One of Euclid's primary scientific goals is to constrain the equation of state of dark energy, the mathematical description of how its density changes as the universe expands. The standard model assumes that dark energy is a cosmological constant, that its density remains perfectly stable as space expands, and that its influence on cosmic expansion is uniform and predictable. But Euclid's latest measurements of galaxy clustering at different cosmic epochs are producing attention. The rate of structure growth in the early universe and the rate measured at intermediate distances are not matching as cleanly as the models predict. The discrepancy is small. It is not yet at the threshold scientists demand before calling something a confirmed discovery, but it has grown since the first data release. And attention that grows with more data is not noise, it is a signal. If dark energy is not constant, the implications extend far beyond cosmology textbooks. A dynamic dark energy would mean that the force driving the accelerated expansion of the universe is evolving, changing its character over cosmic time. It could grow stronger. It could weaken. In extreme theoretical scenarios, a strengthening dark energy density could eventually overcome all other forces, first shredding galaxy clusters, then galaxies, then star systems, then atoms themselves in what physicists call the Big Rip. Euclid is not confirming that scenario, but it is, for the first time, providing data precise enough to test whether we are moving toward it. The universe's fate is no longer just philosophy. Euclid is turning it into measurable science. Beyond the grand cosmological questions, Euclid's newest images are exposing unsettling details at smaller scales that challenge a different set of assumptions. In a series of observations targeting dwarf galaxies in the local cosmic neighborhood, Euclid's infrared sensitivity has resolved stellar populations that were previously invisible. And the mass-to-light ratios being measured in these dwarf galaxies are extreme. Some of these small systems appear to contain far more mass than their visible stars can account for, even after accounting for expected dark matter fractions. The excess is significant. It suggests either that these dwarf galaxies are embedded in dark matter halos of extraordinary density, or that something about the gravitational behavior in low-mass systems deviates from what our standard model predicts. Both possibilities are deeply uncomfortable. The first implies dark matter is even more concentrated than expected at small scales. The second implies that gravity itself may behave differently in low-density environments than our equations describe. That second possibility connects to one of the most persistent theoretical tensions in modern physics. Modified gravity theories, which propose that Einstein's general relativity requires adjustment at certain scales or densities, have long been considered fringe ideas struggling to match cosmological observations. But Euclid's data, accumulating across multiple independent measurements now, is beginning to show systematic patterns that modified gravity theorists predicted, and standard dark matter models did not. No single measurement is decisive, but the patterns are becoming harder to dismiss. Euclid may be quietly building the case that our theory of gravity, the most precisely tested theory in the history of science, is incomplete. Not wrong in everyday situations, but incomplete at the scales where the universe's largest decisions are made. What makes Euclid's latest images truly terrifying in a scientific sense is not any single anomaly. It is the convergence. Multiple independent observations, targeting different regions, using different measurement techniques, are producing results that all point in the same uncomfortable direction. Dark matter behaves in ways that exceed our models. Dark energy may not be constant. Structure formed more aggressively than our simulations reproduce. Gravitational signals appear without visible sources, and regular geometric patterns exist inside cosmic filaments that have no theoretical explanation. One anomaly is a curiosity. Two is a coincidence. 5, converging on the same conclusion from different directions, is a pattern that demands attention. And yet, we have seen less than 10% of what Euclid will ultimately deliver. The telescope is operating on a 6-year mission timeline, and the data pipeline is only beginning to process the full depth of its observations. Every anomaly visible today in this small fraction of the total survey will either be confirmed, refined, or overturned by the vastly larger datasets still coming. If these patterns hold and the converging signals across multiple measurements suggest they will, the full Euclid map may not just challenge our cosmological model, it may require its replacement. There is something deeply important to sit with here that goes beyond the technical details. Euclid is not sending back images of catastrophes or cosmic explosions. It is sending back images of structure, invisible structure. Patient, ancient, perfectly organized structure built from something we cannot see, governed by forces we cannot touch, operating according to rules we are only beginning to suspect. The universe in Euclid's images is not violent. It is relentless. It has been arranging itself with geometric precision across billions of years, and it did not need our awareness to do so. That indifference is what makes it genuinely unsettling. We are not observers of a universe that performs for us. We are passengers inside a structure that was fully built before we arrived and will continue reshaping itself long after we are gone. Every galaxy you have ever seen in a photograph, including our own Milky Way, is a secondary consequence of processes driven by invisible physics. We are not at the center of anything. We are not even made of the dominant material. Everything you can see, everything science has ever directly touched or measured accounts for roughly 5% of what the universe actually contains. Euclid is mapping the other 95%. And what it is finding suggests that the other 95% is not a passive backdrop. It is the author of everything. These images were captured 7 minutes ago in astronomical terms. In reality, they are snapshots of a universe that has been evolving for 13.8 billion years, according to rules that may be different from every equation we currently consider fundamental. We are at the edge of a revision, one of those rare moments in scientific history when a new instrument does not just expand our knowledge, but forces us to question the foundation on which all previous knowledge was built. What unsettles you most about what Euclid is revealing? Is it the dark matter halos with no galaxies inside them? The geometric patterns inside cosmic filaments? The growing tension around dark energy? Or simply the realization that the universe has been building something vast, precise, and invisible all around us for longer than Earth has existed, and we are only now, barely, beginning to see it? Leave your answer below. Share this with someone who needs to understand what is actually happening at the edge of human knowledge right now. And if you want to be the first to understand what Euclid reveals next, because what is coming in the remaining 90% of its survey will be unlike anything we have discussed tonight, make sure you are subscribed. The universe is not waiting for us to catch up, but we can try.